In this episode, we're going to take the stress out of two of the most common automation failures you'll meet early on: syntax errors and undefined variable errors. These are the kinds of problems that can make a brand new learner feel like the computer is being petty because the fix can look small while the error message looks loud. The reality is that these failures are often the easiest to solve once you learn a calm, repeatable way to read what the system is telling you. Syntax errors are about the shape of what you wrote, meaning punctuation, structure, and grammar rules of the language or template you're using. Undefined variable errors are about missing information, meaning the code is asking for a name or value that does not exist in the place it expects. When you stop guessing and start validating step by step, both categories become predictable and, most importantly, fast to repair. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. The first habit to build is to separate what you think the code means from what the parser is actually able to understand. Computers are not reading for intent, they are reading for structure, and structure is incredibly literal. A syntax error usually means the parser hit a point where it could not continue because the rules were broken, like a missing closing bracket, a misplaced comma, or an unexpected character. When you see a syntax error, resist the urge to scan randomly for something that looks wrong, because your eyes will lie to you when you are anxious. Instead, treat it like a map problem where you trust coordinates more than vibes. The message often includes a line number, a column, or a nearby token that triggered the failure, and those details are clues about where the parser got confused, not necessarily where you made the original mistake. The operational goal is to locate the exact place the parser lost the plot, and then walk backward to find the earlier mismatch. A useful way to understand syntax errors is to picture the parser building a stack of expectations as it reads. If you open a parenthesis, it expects a closing parenthesis later, and it keeps that expectation in memory. If you open a brace, it expects a closing brace, and if you start a block, it expects the block to end. Many syntax errors are not wrong characters so much as unfulfilled promises, where you opened something and never properly closed it. That is why the error may appear on a line that looks fine, because the problem is actually that the parser was waiting for something that never arrived. This is also why indentation and whitespace rules can matter so much in some formats and languages, because whitespace is part of the structure, not just styling. When you adopt this model, you stop treating syntax errors as mysterious and start treating them as accounting errors in structure. Your job becomes reconciling the opens and closes until the structure balances again. Another habit that prevents guessing is to reduce the problem to the smallest failing unit you can inspect. If a file is long and you see a syntax error, the worst move is to start changing multiple lines at once, because you won't know which change fixed the problem or which change created a new one. Instead, think like a careful mechanic and change one thing, then recheck, then move to the next hypothesis. If you can validate the file in a way that checks structure without executing full automation, do that, because you want quick feedback. Even without any special tooling, you can still do a manual version of reduction by focusing on the region around the reported line and confirming each structural element. Count opening and closing delimiters, confirm separators are consistent, and check that blocks are properly ended. Small, controlled steps are the opposite of guessing, and they create confidence that you understand the failure rather than accidentally stumbling into a fix. Now let's shift to undefined variable errors, because they often feel different emotionally even though they are just as logical. An undefined variable error means the code tried to look up a name and did not find a value at the moment it needed one. Beginners sometimes interpret that as the variable not existing anywhere, but more often it exists somewhere, just not in the scope the code is currently using. Scope is the set of places a name is visible and valid, and it changes depending on where the name is defined and where it is referenced. Another common cause is a typo, where you defined one name and referenced a slightly different name, which the computer correctly treats as a completely different identifier. Undefined variable errors also happen when you assume a value will be provided from the outside, like an environment setting, a configuration file, or a pipeline, but it never arrives. The operational mindset is to treat undefined variables as missing inputs or mismatched names, not as a reason to start inventing values on the fly. A calm troubleshooting approach begins with reading the error message as a statement of fact, not as an accusation. It is telling you which name was missing and where the code tried to use it, and that is enough to start a disciplined search. Your first question should be, where is this variable supposed to come from? Because every variable has an origin story. Some are declared locally in the same file, some are passed into a module or template, some come from shared configuration, and some are derived from earlier logic that might not have executed. Once you identify the expected source, confirm whether that source is actually active for the run you are doing right now, not for the run you imagine. Many undefined variables happen because someone assumed a default exists, or assumed a file is always loaded, or assumed a certain environment always provides values. Your job is to verify the chain of custody for the variable from definition to reference, without filling gaps with assumptions. It also helps to distinguish between a variable that is truly undefined and a variable that is defined but empty or null, because they fail differently. Undefined means the name itself cannot be resolved, like calling for a person who was never invited to the meeting. Empty means the name exists but carries no useful value, like the person showing up but bringing no information. Some systems treat these similarly and others treat them differently, but operationally you want to know which one you have. If it is undefined, you focus on where it should be defined and why it is not available in scope. If it is empty, you focus on why the expected data did not populate, such as a missing lookup result, a conditional path that skipped assignment, or a data source returning nothing. Beginners sometimes try to solve empty values by renaming variables, which does nothing, or they solve undefined variables by hard-coding a value, which hides the real issue. The predictable path is to identify whether the failure is about name resolution or about value content. Name mismatches deserve special attention because they are both common and easy to miss. Humans see names as similar, but computers see them as exact strings, which means small differences matter. Case sensitivity can turn a name into a different name, and so can underscores, hyphens, or pluralization. Even a trailing space in a copied identifier can create a ghost variable that never matches the real one. That is why it is so important to copy carefully and to keep naming conventions consistent within a project. When troubleshooting, do not rely on visual similarity. Instead, compare names character by character, especially around common trouble spots like prefixes and suffixes. If you are using an integrated development environment, IDE, take advantage of features that show where a name is defined and all the places it is referenced, because that helps you spot the one reference that does not match the others. The operational outcome you're aiming for is a single, consistent identity for each variable across all the places it is used. Another major cause of undefined variables is misunderstanding how data flows between layers, especially when templates, modules, and configuration are involved. A variable can exist in one layer and be invisible in another, which can feel unfair until you remember that boundaries exist for a reason. A template might only see values explicitly passed to it, and a module might only see inputs declared as parameters, even if other values exist elsewhere. Beginners often assume everything can see everything, but that assumption breaks quickly as systems grow. The fix is not to weaken boundaries, but to make data flow explicit so it is clear what is required and what is optional. In operations, explicit inputs are safer because they force you to provide what is needed, and they make it easier to spot missing values early. When you make inputs explicit, undefined variables turn into predictable validation failures instead of late surprises during a run. That predictability is the opposite of guessing, because you are designing the system to tell you what it needs. Syntax errors and undefined variables also interact in a way that can confuse you if you do not expect it. A syntax error can prevent a file from loading, and if the file fails to load, variables you thought were defined in that file never become available. Then you see undefined variable errors that are secondary symptoms, not primary causes. The disciplined approach is to fix syntax issues first, because syntax issues can block the entire evaluation process. Once the code can be parsed cleanly, then you can trust undefined variable errors to be real signals about missing values. This ordering matters operationally because it prevents you from chasing the wrong problem. It also reduces the temptation to apply quick hacks like duplicating definitions in multiple places, which can create long-term confusion. Clean parsing is the foundation, and only after you have that foundation should you troubleshoot missing values and data flow. A systematic workflow for both error types is to verify in layers, starting with the simplest, most mechanical checks. For syntax, confirm the file is structurally valid, confirm delimiters match, confirm blocks are properly ended, and confirm separators are consistent. For undefined variables, confirm the variable name exactly matches its definition, confirm the definition is actually loaded in the current run, confirm the variable is in scope where it is referenced, and confirm the value is present when needed. At each step, you are asking a question that has a yes or no answer, not a vague feeling. That yes or no structure is what keeps you out of guessing mode, because guessing thrives on questions like what do you think is wrong, which have no clear end. The fastest troubleshooters are not magical, they are methodical, and they use simple checks to eliminate possibilities. The goal is not to be clever, it is to be repeatable under pressure. It's also worth learning to interpret error messages the way they were intended, because they often contain more help than beginners realize. A syntax message that mentions an unexpected token is telling you what the parser saw and did not expect at that location, which points you toward a mismatched delimiter earlier. A message that points to end of file often means something was left open and the parser reached the end while still expecting closure. An undefined variable message often tells you the name and sometimes the context, which can reveal whether the system expected a local variable, a parameter, or a property within a data structure. If you see a message that references a property access, it may mean the variable exists but the subfield does not, which is a data shape problem rather than a simple missing variable. When you treat messages as diagnostics, you stop taking them personally and start using them as the shortest path to the root cause. That shift is crucial for operational confidence because it replaces frustration with a clear next action. One practical technique that helps both categories is to keep changes small and to confirm behavior after each change, especially when you are working in shared automation. In team environments, a guessing-based fix can introduce a new error that only appears later, and then everyone spends time untangling what happened. Small, verified changes reduce that risk and make it easier to roll back if needed. They also produce cleaner history, which matters when you're tracking how a system evolved and why a certain decision was made. If you are troubleshooting under time pressure, you still want to preserve discipline because rushed, sweeping edits can make the situation worse. A calm pattern is to identify the likely smallest fix, apply it, validate, and only then move to the next issue. This approach also trains you to trust evidence over intuition, which is the foundation of safe, predictable automation work. Finally, connect all of this back to the operational outcomes you care about: safe reruns, predictable behavior, and reparable automation. Syntax correctness ensures the system can even read your intent, which is the first gate to reliability. Proper variable definition and scope ensure the system has the information it needs to build the right outcome, which is the second gate to reliability. When those gates are strong, failures become more meaningful because they reflect real environment issues rather than simple mistakes in the code structure or missing inputs. You also become faster because you stop making random edits and start using a repeatable diagnostic path that works across languages and formats. The deeper win is confidence, because you learn that errors are not chaos, they are signals. When you can troubleshoot syntax and undefined variable errors without guessing, you turn early automation frustration into a steady skill that scales with every new project you touch.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.